Hello everyone, and welcome to the Hidden Truths, a place where we explore scenarios, histories, and truths hidden from the public view. Big thanks to Cirnosad for compiling this. We are going to take a step back from nuclear weapon design to look at conventional bombs. You'll appreciate the engineering challenges facing designers and how they optimize the devices. In the previous installment, we learned all about nuclear reactions and the energy produced by them. We also spoke briefly about one chemical reaction and the energies associated with it, but we never discussed what energy is. Energy is essentially an abstraction of transference of states between entities in our world, and we have a particle to denote this transference, the photon. In Poincare's framework, we call energy a convention. The process exists, but underlying phenomenon is up to modeling. Photons mediate energy transitions from both the nucleus and the electron cloud. In everyday life, you know roughly what energy is. You eat food, you get energy, you can then move around. You might even gain some weight if you're not careful. And if you exercise, you might even lose some. In the particle realm, it's really no different, but we know some rules. As we learnt before, energy and mass are kind of equivalent, though hadron count, etc. has to be maintained, but let's touch that for now. In our reactions, we had to balance the energy of both sides to find out the total energy released. This is the conservation of energy and mass. But there is one other conservation rule we have to take care of, the conservation of momentum. What is momentum? Well, simply put, it is the weight of your motion, specifically the mass of a particle multiplied by its velocity. You can try this at home with 3 coins. Place your finger on the middle coin, place one coin opposite the other, still touching that coin, and push the further coin into the one you're holding. It should move. And momentum, i.e. velocity of a particle, is associated with kinetic energy. That's right, not only can energy be used to transition the state of electrons around the electron cloud, it can also change the velocity of a particle. Well, as long as conservation of momentum is achieved. Here's a very instructive example. When a stationary bomb detonates, it breaks up and flies out in all directions. It has to. Were the bomb to move a single direction, momentum would not be conserved. But why does it have to move? Why can't it just sit there and heat up? At a very slow time scale, when the chain reaction begins, indeed there is a rapid release of energy. But other byproducts, namely gases, often oxygen, as the reaction proceeds, there is a buildup of gases and the pressure increases. This is where we enter thermodynamics. You see, we're kind of dealing with individual particles. It's kind of impossible. Even a gram of flour contains more particles inside than you can practically simulate, let alone track, on a computer in a lifetime. So we need some new abstractions: volume, pressure, and temperature. Volume is somewhat self-explanatory, but note that it can change dynamically and quite dramatically in some cases. One easy way to understand pressure is the force a gas applies in a container. Think of what you feel when you crank a bicycle pump. The more particles of gas in a given volume, the more pressure. But there's also the temperature to consider. The temperature is the average kinetic energy in a state. Most of this would be in things like vibrational, rotational, excitement, but they're all contained energies. It's very complicated. But for our purposes now, until we enter plasmas, we just need to understand that temperature is stored energy. The more energy a gas absorbs, example from an ongoing chain reaction, the more the temperature builds up. This means the force will build up as well. Consider a silly block of classic explosives, which has a silly burning soot landing on it, starting a chain reaction. The explosive begins to detonate, generating internal gases. The still solid parts of the explosive begin to experience immense forces. Very quickly, they break. In this case, we have an incomplete explosive. We allowed the volume of the primitive explosive device to change to the point where it broke apart, and not all the material contributed to the chain reaction, or it diffused over an ineffective area. This is a basic blast device. Can we make this relic more useful? Of course we can. We can hold the damn material together for long enough by using a strong material casing, such as steel. This would delay fragmentation until everything explodes. We can then use a fuse to set the fire up from a distance. We can also make it safer. We wouldn't want random soot to detonate it, right? That's why bomb engineers distinguish the primary material from the secondary primer, higher sensitivity material that can initiate the detonation. Here is an example from the Ming Dynasty. Just to finish up this example, you really don't want to be lighting fires just before using an explosive charge in modern wars. You want things to be timed based on events. Thus, military engineers use a fuse. Not a fuse, it's a fuse with a Z. Basically an electronic or mechanical detonator. Thus, we have all the ingredients for a modern blast or fragmentation bomb. We have an explosive source that generates both heat and gas, and a casing which allows the reaction to complete before blowing apart. Very often, the casing is used as the primary lethality effect object. Let's summarize how this device works. A primer detonates with a large energy that creates a chain reaction wave, a shock wave, that flows throughout a main filling, which then reacts to completion, producing hot gases that blow apart the bomb's casing, flying in all directions. Aside, notice the white smoke that fills the space during an explosive event. This is the gas you spoke of before exploding out in all directions. It's a very hot gas and creates a shockwave that can kill you instantaneously if you're in the kill zone, and damages everything else around it. It is important to note that there are different kinds of explosive devices, each suited for a different mission, which we will quickly cover for completion. There's a shape charge, which is what you see here. A shape charge introduced an asymmetry to drive metal to high speeds and temperature, taking at most half of the momentum, using it to blast through some thick armor from the sheer speed and temperature of the penetrator. It is important to discuss the fusing as well. These have gotten very advanced over the years. It is said that the impact fuse won the US World War II, not the new nuclear bomb, and we do agree here. What you see is one of the US military fuses. This explodes before even hitting the hill that it is being shot at. Thanks to the advances in technology, it became possible to create a new kind of thermobaric bomb that uses a delicate primer plus timed fuse and a tertiary igniter to first spread the fuel around an area, then detonate it all at once to create a deadly shockwave. Now, how far can we scale these bombs up? What's the largest conventional bomb other than the FOAB, which is in its own special category, but still rather small at a maximum of 40-ton equivalent of TNT? That destination would go to the MOP. The warhead on the MOP contains a 24,000 kilogram explosive, but the bomb itself is 14,000 kilograms. What gives? Well, you see, in its specific mission, the casing has to be extremely strong. In fact, there's a practical limit with conventional bombs due to the sizing of the required casing. Too large a casing and you start to attenuate the explosive shockwave. Naturally, you simply cannot begin to approach the explosive power of a nuclear bomb just by making a single giant bomb. But what about many smaller bombs detonated together? Enter Operation Sailor Hat. In this test, the US military stacked 500 short-ton explosive charges of TNT in a hemisphere and used some precision electronics to have them detonate all at the same time, faster than what a conventional shockwave would do. As you can see, the half-kiloton explosive created a massive shockwave, similar to that you would see in a low-yield nuclear bomb. You see the mushroom cloud as well, and most importantly, the symmetry of the explosive. There's a few things you don't see, however, and we'll get to that later, but the key point I want you to take away from this is the difficulty in producing this symmetrical explosion and the deliberation required. You see, miss the timing and the destruction won't explode in unison. Configure the shape incorrectly, the shockwave will not be symmetrical and will begin to cancel itself out, attenuating the explosion in the center or making it directional. Notice the total lack of stringers. These stringers are a key tell in an unorganized, non-deliberate depot explosion. They can be caused by a variety of reasons. Simply hot fragments of unexploded pieces of ordnances is one reason. Also note the shockwave is visible thanks only to water vapor in cases. And well, that's all for Physics 002. I hope you got a lot out of it and it took some notes, because things are going to get very serious with Physics 3. Until next time, stay cool.